Golden Iris Productions presents a multi-scale action-structured framework relating gravitational and electromagnetic acceleration. Part 3, based on the paper by Mark F. Dennis.
In Part 2, we moved beyond structural comparison and into interpretation. We examined how the repeated patterns across classical, electrogravitic, and emergent formulations point toward a common underlying mechanism. Rather than treating acceleration as the result of distinct forces, we explored the idea that it arises from structured variations within the vacuum itself. By analyzing both macroscopic gravitational systems and microscopic quantum systems, we saw that differences in behavior can be understood as scale-dependent expressions of the same foundational components. In this view, coupling strength, spatial scaling, and vacuum response are not independent features, but interconnected elements of a single action-based framework. This perspective suggests that what we observe as gravitational and electromagnetic acceleration may reflect a deeper geometric and temporal structure embedded within the vacuum.
Microscopic scale, electron at the Bohr radius. Using the classical quantum acceleration expression, A micro classical equals kq squared over MEA naught squared, and substituting standard values for Coulomb's constant K, electron charge Q, electron mass ME, and Bohr radius A naught, the resulting acceleration is A micro approximately 9.04259 times 10 to the 2 meters per second squared. This value represents the angular centripetal acceleration required to maintain the electron in orbit at the Bohr radius. It reflects the extremely strong electromagnetic coupling and the very small confinement scale characteristic of the quantum regime. Macroscopic scale, gravitational field at 20 million meters. Using the classical gravitational expression, A macro classical equals gm over r squared, and evaluating at a radial distance of r equals 2 times 10 to the 7 meters from the center of the Earth, the resulting acceleration is approximately A macro approximately 0.91 meters per second squared. This value corresponds to the gravitational field strength at medium Earth orbit and demonstrates the comparatively weak large-scaled interaction when distributed over macroscopic distances.
Electrogravitic model evaluation. Using the macroscopic electrogravitic formulation, A subscript EG equals 1 over 2r epsilon naught u naught with 1 minus epsilon naught over epsilon local, with the defined constants. Epsilon naught equals 8.85419 times 10 to the minus 12, U naught equals 1.25664 times 10 to the minus 6, and local permittivity. Epsilon local equals 8.85418788207 times 10 to the minus 12. The deviation term evaluates as 1 minus epsilon naught over epsilon local equals 1 minus 8.85419 times 10 to the minus 12 over 8.85418788207 times 10 to the minus 12. When substituted into the full electrogravitic kernel and evaluated at the specified radial parameter r, the resulting acceleration is g equals 0.908316 meters per second squared. This value represents the effective gravitational acceleration produced by the electrogravitic model under the specified vacuum parameters, where variations in local permittivity govern the modulation of the vacuum response field.
Within this framework, the acceleration exhibits an effective dependence on the radial structure of the kernel, with the overall scale and sign determined by the relative vacuum deviation term epsilon local, which encodes spatial variation in vacuum properties between regions of differing energy density. At the microscopic scale, this deviation term produces a significantly amplified response due to the additional 1/r² scaling, resulting in strongly localized field behavior, while at the macroscopic scale, it contributes only a small correction to the classical gravitational value, consistent with weak field behavior dominated by 1/r type dispersion.
Microscopic electrogravitic acceleration. Including the microscopic electrogravitic scaling factor, the acceleration is given by A micro script Eg equals 1/2r epsilon naught u naught times 1 minus epsilon naught over epsilon local times 1.99964 over r squared. Rearranging radial terms, A micro script Eg equals 1.99964 over 2 epsilon naught u naught times 1 minus epsilon naught over epsilon local times r cubed. Using the defined vacuum parameters, epsilon naught equals 8.85419 times 10 to the minus 12, u naught equals 1.25664 times 10 to the minus 6, epsilon local equals 8.85465933396 times 10 to the minus 12, the microscopic electrogravitic acceleration evaluates at the Bohr radius r equals a naught to A micro script Eg equals 9.04259 times 10 to the 22 meters per second squared. This result reflects a strongly amplified acceleration at atomic scales arising from the combined effects of the vacuum response kernel and the effective 1/r³ spatial dependence, which produces extreme localization of the field gradient in the quantum regime.
Macroscopic electrogravitic acceleration. A macro Eg equals 1/2r epsilon naught u naught times 1 minus epsilon naught over epsilon local. Using the same vacuum parameters, the macroscopic electrogravitic acceleration becomes A macro Eg approximately equals 1 minus epsilon naught over epsilon local divided by 2r epsilon naught u naught. At large radial distances r, this produces a small correction to the classical gravitational field, consistent with weak field behavior, where spatial dispersion dominates, and vacuum response variations act only as perturbative modulation. Emergent model evaluation. Using the microscopic emergent acceleration, acceleration micro to the em equals q squared over 4 pi epsilon naught me a naught squared. Substituting known constants, q equals 1.602 times 10 to the negative 19, epsilon naught equals 8.85419 times 10 to the negative 12, me equals 9.109 times 10 to the negative 31. A naught equals 5.29 times 10 to the negative 11. Yields acceleration micro to the em approximately 9.04 times 10 to the 22 meters per second squared, which matches the classical quantum result, confirming structural equivalence at the microscopic scale.
Using macroscopic emergent acceleration, our macro em equals 4 pi Lp squared AME over epsilon naught U naught squared Q squared R squared. Lp equals 1.616 times 10 to the minus 35. epsilon naught equals 8.85419 times 10 to the minus 12. U naught equals 1.25664 times 10 to the minus 6. The expression shows that the numerator contains extremely small Planck scale terms, while the denominator contains squared vacuum and charge terms, producing a highly suppressed acceleration, consistent with macroscopic gravitational magnitudes when evaluated over large R. G equals 0.908316 meters per second squared.
Interpretation of numerical results. The comparison between 9.04259 times 10 to the power 22 meters per second squared and 0.91 meters per second squared demonstrates the extreme disparity between quantum and gravitational scales. Within this framework, this difference arises from spatial scale differences, A0 versus R, coupling strength redistribution, vacuum parameter scaling. Despite this disparity, all three model classes preserve a consistent structural form, supporting the interpretation that both regimes are governed by a shared action-based system with scale-dependent parameter weighting.
Emergent model evaluation. The emergent formulations A macro implies EM equals 4 pi LP squared AME over E naught U naught squared Q squared R squared. A micro implies EM equals Q squared over 4 pi E naught ME A naught squared demonstrate that both regimes preserve the same structural dependence on vacuum parameters, geometric normalization, and coupling terms. When evaluated numerically, the microscopic expression reproduces the same order of magnitude as the classical quantum acceleration, while the macroscopic expression yields a scaled-down value consistent with gravitational observations when appropriate effective parameters are chosen.
Structural correspondence between macro and micro regimes. A direct comparison of these formulations reveals that, despite differences in scale and interpretation, the same classes of terms recur across all equations. Radial dependence appears either as inverse square spatial dispersion in the macroscopic domain or as confinement scaling in the microscopic domain. Coupling terms appear as mass in gravitational systems and charge in electromagnetic systems, while inertial resistance is encoded through mass parameters such as ME. Vacuum parameters, particularly epsilon naught and related quantities U naught, appear in both regimes, suggesting that the vacuum itself plays a mediating role in determining acceleration. Geometric normalization factors, including 4 pi, further indicate that spherical symmetry and boundary conditions are embedded directly into the structure of the equations. Although the equations differ in form, their components serve consistent functional roles, indicating that the distinction between gravitational and electromagnetic behavior may arise from scale-dependent expressions of a shared structural framework rather than from fundamentally separate mechanisms.
Action-structured interpretation of acceleration. Within the present framework, the equations are interpreted as encoding the action principle directly through their structure. Each term contributes to a spatial and energetic variation that defines the system's evolution. Rather than introducing an external Lagrangian and deriving equations of motion, the acceleration expressions themselves are viewed as compact representations of underlying action variation. Spatial parameters such as R and A0 define gradients across which field quantities vary. Coupling constants determine the strength of interaction between sources and fields, while vacuum parameters define how these interactions propagate. The resulting acceleration emerges as a response to these combined variations, representing a tendency toward extremization within the system. This interpretation extends naturally across both macroscopic and microscopic domains, suggesting that the same action-based mechanism governs behavior at all scales, even though the dominant terms differ.
Energy-time gradients and vacuum structure. A central feature of this framework is the interpretation of acceleration as arising from gradients in an underlying energy-time structure associated with the vacuum. Differences between spatial regions correspond to differences in effective energy density and, when compared across reference frames, to differences in the rate of temporal progression. Objects of mass therefore follow trajectories consistent with transitions from higher energy, faster evolving states toward lower energy, slower evolving states. This behavior aligns with gravitational attraction in the macroscopic domain and bound state dynamics in the microscopic domain. Locally, physical laws remain unchanged, but relative comparisons between regions reveal structured variation consistent with relativistic effects.
In the quantum regime, electromagnetic fields produce strong, localized gradients, while in the macroscopic regime, these effects are distributed and appear weaker. The apparent absence of strong electromagnetic forces at large scales is interpreted not as a disappearance of underlying fields, but as a cancellation or redistribution of opposing components, leaving a residual effect that manifests as gravity. Within this view, the vacuum is not empty, but contains an underlying energy structure that participates in the dynamics of the system. Variations in this structure, including what may be described as zero-point energy differences, contribute to both linear acceleration and orbital motion. Orbital behavior, in particular, is interpreted as a natural consequence of lateral and angular responses to these gradients.
Conclusion. The comparative framework presented here demonstrates that classical gravitational, electrogravitic, and emergent acceleration laws share a common structural foundation across both macroscopic and microscopic regimes. Without reducing their forms, each equation can be interpreted as encoding an action-based mechanism in which spatial variation, coupling strength, and vacuum structure combine to produce acceleration. Across scales, consistent functional roles are observed for geometric, coupling, and vacuum-related terms, suggesting that gravitational and electromagnetic phenomena may represent different manifestations of a shared underlying field structure. Within this interpretation, acceleration arises from gradients in an energy-time structure embedded in the vacuum, and the equations themselves describe both the magnitude and the origin of motion. While speculative, this framework provides a basis for further exploration of the relationship between quantum and gravitational systems through a unified action-structured perspective, preserving the full complexity of the governing equations while revealing their deeper structural correspondences.